Welcome to this explainer on control systems architecture, prepared by Dr. Nima Hadian. Today, we're going to completely unpack the exact mathematical synthesis of industrial PID controllers. We're sticking strictly to the source material here to give you a really robust, academically sound breakdown. So let's just dive right in.
Our pipeline for today is structured into three rigorous sections. First up, target and synthesis. Second, roadblocks and architecture. And third, industrial deployment. Okay, section 1, target and synthesis. This is where we define our end goal and extract the foundational mathematical controller. Think about the stark contrast between a completely chaotic, uncontrolled system and a smooth, predefined trajectory. Our fundamental objective here is to mathematically force the controller parameters to match that desired state. By defining what we want right from the start, we entirely eliminate the guesswork of blind tuning. No more trial and error, just exact science. To do this, we need to look at the standard unity feedback architecture. Our mathematical goal is to isolate and define GC of S, that's our controller, from within this unity feedback system. In this equation, the output, Y of S, is a function of the physical process G of S, our controller GC of S, and the input R of S. It's like a giant puzzle, and GC is the missing piece we need to solve for. We simplify this entire closed-loop system into one single target expression, which we'll call G_desired of S. The logic here is absolutely airtight. If the physical output behavior, Y of S, exactly matches our desired behavior dictated by G_desired of S times the input R of S, then the system is perfectly synthesized. So how do we get there? We reverse engineer it. By taking that closed-loop transfer function and algebraically solving specifically for GC, we arrive at a really powerful takeaway. If we have an exact mathematical model of the physical process G, and we've defined our ideal goal G desired, the mathematical model of the required controller GC can be directly extracted. The math works out so that GC equals 1 over G, multiplied by the quantity of 1 over the inverse of G desired minus 1. Now, for most industrial processes, we mandate a second-order response. This gives us our target equation, where G desired of S equals 1 divided by the quantity of tau R squared times S squared plus 2 times tau R times zeta R times S plus 1. Basically, this curve gives us a nice stable approach to our set point without any crazy oscillation. But we have to be careful not to place overly aggressive constraints on the physical system. To prevent that, we decode our target parameters from that second-order equation. First, we set the damping ratio, zeta R, to be critically damped, where zeta equals 1, or just slightly underdamped. Then we use the time constant, tau R, as the speed governor for the closed-loop system. It defines our desired speed, where tau R equals 1 over omega n. Having nailed down our target, we have to look at the physical plant itself. We model the process G of S as a third-order system. Think of 3 interacting tanks. The equation for G of S is K divided by the product of tau 1 S plus 1, tau 2 S plus 1, and tau 3 S plus 1. Now, here is the absolutely crucial constraint. Unlike our target parameters, tau 1, tau 2, and tau 3 are fixed, unchangeable properties of the physical hardware. We literally cannot change them. If we feed our physical process model, G of S, and our defined target, G_desired of S, into our reverse-engineered equation, we get the raw synthesized controller G_C of S. Now, evaluating this reveals a massive catch. This expression is mathematically perfect for achieving our goal, but structurally, it's highly problematic for real-world deployment. To reorganize this complex, messy equation into something practical, we substitute our target parameters into some new variables. Let's define phi as tau R divided by 2 zeta R. And we'll define beta as 2k tau R zeta R. By subbing phi and beta back into our denominator, we clean up the math significantly. This rearranged GC of S equation is much easier to manage. Which brings us nicely to section 2, roadblocks and architecture. This is where we take our theoretical math and adapt it to fit standard PID structures. Remember that structural roadblock I just mentioned? Well, here it is. The raw output we just synthesized does not match standard industrial PID configurations. Sure, a custom digital controller could run this exact third-order math, but let's be real. The global manufacturing industry relies on standardized PID architecture.
so we're the ones who have to adapt our math to fit the industry standard. To make this work, we use the art of cancellation. By intentionally adjusting our desired tuning parameters, tau r and zeta r, we force a near match where phi is approximately equal to tau 3. This deliberate mathematical approximation is a total game changer. It allows us to completely cancel out the complex, non-standard time constant terms in the numerator and the denominator, specifically the tau 3s plus 1 and the phi s plus 1 terms. And that strategic cancellation is our victory condition. By eliminating that third-order complexity, we yield a standardized G of CS output. The equation simplifies beautifully to tau 1s plus 1 times tau 2s plus 1, all divided by beta s. This newly refined structure now perfectly mirrors a classical industrial PID. Our next critical step is to map this. We take the target architecture equation for a standard PID controller defined by proportional gain K sub p, integral time Ti, and derivative time T sub d. The target PID architecture is G PID of S equals K sub p times the quantity of 1 plus 1 over T sub I s plus T sub d s. We just need to map our newly synthesized mathematical model directly onto these standard parameters. By directly comparing our synthesized model to that target PID equation, we derive the exact tuning coefficients. Proportional gain Kp equals tau 1 plus tau 2 over beta. Integral time Ti equals tau 1 plus tau 2. And finally, derivative time Td equals tau 1 times tau 2 divided by tau 1 plus tau 2. Just like that, we've successfully translated theoretical synthesis into exact standard coefficients. Finally, we hit section 3, industrial deployment. Let's move beyond the theoretical tuning and see how this plays out with physical hardware realities. Moving beyond the textbook means facing facts. Theoretical math assumes ideal conditions, but on the factory floor, industrial processes are nonlinear, unpredictable, and highly complex. To actually apply our derived parameters, we need to understand how industry physically adapts these textbook equations inside real control rooms. You absolutely have to understand the 90% rule. Even though there are vastly more complex control systems out there, the basic PID family, proportional, integral, derivative, acts as the primary control structure for over 90% of industrial controllers worldwide. It's wild, right? But it's used everywhere because of its simplicity, its operational efficiency, and its relentless reliability. But here is the massive industrial paradox. Despite being everywhere, more than 80% of PID controllers are improperly tuned in the field. Basically, the industry is mostly just winging it with trial and error. Closing this optimization gap demands that operators understand the mathematical synthesis and the specific terminology that dictates true optimization. To communicate effectively with these systems, we need to speak the industrial vocabulary. Textbooks use proportional gain, Kc. But industrial control rooms often tune using proportional band, or PB. Proportional band is defined exactly as the range of error required to drive the control output from 0% to 100%. Mathematically, PB equals 100 divided by Kc. Translating these terms properly is a big deal, and getting it wrong can be catastrophic. Proportional gain is the textbook mathematical standard. A higher value means higher sensitivity and more aggressive control. But proportional band, the industrial standard, is inversely proportional. A smaller value means higher sensitivity. So a tiny 10% proportional band means a very small error will trigger a massive, immediate reaction in your system. To wrap this all up, let's quickly recap our 5-step pipeline. Step 1, define your target, G desired. Step 2, extract the raw GC through synthesis math. Step 3, use cancellation to approximate phi to tau 3. Step 4, map and derive the standard PID parameters Kp, Ti, and Tb. And step 5, translate all of that into industrial terms like proportional band for factory deployment. By leveraging this direct synthesis math, we approximate gracefully and deploy flawlessly. So my final question for you as future engineers is this: how will you apply this rigorous mathematical extraction to tame the unpredictable chaos of your future factory floors?